All right, good morning, everybody. Can you hear me okay?
Good morning, yeah.
Thanks, Aaron. Good morning. All right, I'm glad to see those of you who have done your assignments or at least attempted them on Admentum. Good job. We should have the first two mastery tests finished so far in Unit 6. Today we'll be doing the next one. Okay, here we go. So this next tutorial, next lesson is called Similarity, Proportion, and Triangle Proofs. So all week long, we've been dealing with dilations and similarity. And today we're going to add in the idea of proportion, or really expand on it, because we've been kind of using that too. And we're going to be working exclusively with triangles. So today we're going to look at two different like rules or mathematical laws that go along with triangles and use similarity. So just recall with me that similar triangles from yesterday means that all angles are congruent or equal and the sides are proportional. So just like with dilations, the sides of the two different figures, two different triangles, will be proportional to each other. And the angles are the same. The angles stay the same. Really quick, let's look at another diagram of that. Let's say we had triangle ABC. I'm going to make it a right triangle. Let's say that this is 60 degrees and this is 30. And then, of course, the little square, that right angle, that means 90, just as a review. So if we were given this triangle and then we were given a second one that was much bigger but had the exact same angles inside, these two triangles are similar. Triangle DEF, we'll call it. And that means that there's some number we can multiply by the little one. We multiply by the scale factor to go from the small to the large. Or we could go the other direction too. It would be a different scale factor. It would be a fraction or a decimal, but there's another number that we could go the other direction. So it just depends on which ones are original and which ones are ending, our dilated version. You can go both ways. It all depends on which one they're telling you you're starting with. So we're going to look at two different rules or theorems that go along with these ideas we've been doing on Monday and Tuesday, and then look at some problems that we can solve using these ideas. Here we go. Okay, the first one is called the triangle proportionality theorem. Proportionality. So triangle proportionality. So we're going to be dealing with two proportional triangles. Let's see what it says. If a line cutting through a triangle is parallel to the third side, then the triangles are similar. So we see the line cutting through the triangle on the diagram is DE, cutting through. If this line that's cutting through the middle is parallel to the third side, So that means not side AB, not AC, not the two that it's cutting into, but the one across from it down here. If those are parallel to each other, then it means the two triangles we see are similar. So little triangle ADE is similar to ABC, the larger one. And that means that the angles inside are all equal or congruent. So angle A is obviously the same as angle A. It's the same exact angle. But that also means that angle D, as in dog, matches with B, as in balloon, below it. And then E and C are also a match with each other. They're equal angles, they're congruent to each other. For this to work, we have to have the line DE that's cutting through it be parallel to BC. So if they don't tell us that, then that doesn't mean that the two triangles are similar. So it's an if then. If this is met, if the line is parallel, the two lines are parallel to the third side, then the triangles themselves are similar. So we've got to look out for that information. And if we have that, then the triangles are similar. And actually, this rule goes the other direction as well, meaning if two triangles are similar, if we're told that these angles, look to the picture on the right, if we're told that angle D is a match with B and we're told that E is a match with C, then we can say the two lines are parallel. So it goes the other direction. Remember this little symbol here? This may come up again. This means similar. So that's telling us a lot of information. It's telling us that the angles are all equal and the sides are proportional to each other, which means there's some scale factor we could use to multiply to the little to get to the big, or the fraction version that we could multiply to the big to go towards the little and find those side lengths. Let's look at a question. Find the missing length. Okay, these two triangles aren't labeled with their vertices, but we see that this is labeled as being 20 units long. That's this stretch right there. And this is 8 right here. This stretch is 18. And then we're supposed to find this unknown one right here. Let's label the different vertices we see so we can talk about it better. So let's call this point A. We'll call this one here B, and then C. And then this spot where the line that's cutting through is intersecting AB, we'll call that D, and we'll call this one E. Okay. Before we get started, I want you guys to practice naming the two triangles. So it's kind of a two-part question. One, do you see two triangles in this picture? Because it does have two, even though it only kind of looks like one. There's a second one hidden there. In the chat, can you name the two triangles for me? And you can just say, you can just address me like directly in the chat if you don't want to address the whole group. So let's start this by naming the two triangles in the chat. I'll change my color. It's kind of hard to see. Name the two triangles in the chat. Remember, we name a triangle with 3 points that make it up. If you don't see two, name one. At least you can see one, I'm sure. So, what are the names of the two triangles? Tell me in the chat. Okay, I see one person responded. Thank you. I want to hear from everybody. If you can't see both triangles, at least tell me one of the triangles that you see. Just practice naming it, okay? I'm not with you in person, so we have to get some practice through chatting.
What if we don't remember the names at all?
We just labeled it Manaya. So you're going to use those letters that I labeled it with to name it. I'm not looking for obtuse or right. That's like a what type of triangle. We're just trying to name it. What is the name of those triangles based on the points that they have, based on those vertices that they have?
It's not that I don't want to chat. I just literally don't know what they're called, to be honest.
Okay. Does anyone see the letters I put on the screen? A, D, B, E, and C?
Yeah, I can see those.
Yeah. Okay, good. So how we name a triangle is using the three letters that make it up. Every triangle has 3 points, 3 vertices. I see 5 of you have typed in something. Thank you. Good job. I want to hear from everybody. So if you know the 3 letters that we name those points on the outside, then that's how we name the triangle. I'm going to give you another example. We'll come back to this. Look at this diagram here on the screen. Here's 2 triangles in red. On the left, we've got triangle ADE. How do we name it? I'm going to write it out. Triangle ADE. On the right, we've got triangle ABC. The 3 letters that you see on the outside, that's how we name it. And that's what I want you guys to practice for this one. Actually, that's going to be similar to the one I just had up because I named them the same. So, what are the names of those 2 triangles? We can't really solve the problem or dissect it or use the theorem that I just had up on the screen if we can't name them. So, we have to start there. Awesome. 7 of you. Thank you. Cool. 8. Good job, guys. Take a risk. Try naming it based on what I just told you. We just use the letters to make it up. And if you can't see 2 triangles, that's fine. But first step would be at least identifying one of these triangles. All right. I want to look and see what you guys have said so far. Awesome. Thank you. Sella, Maria Celeste, Andrew, Antonio. Awesome. Aaron.
I'm sorry, you called me?
Oh, no, I'm just saying thank you for answering, for trying to name the 2 triangles. Good job. All right. So Antonio said ABC. That's one of them. Good. That's the outer, like the larger of the 2 triangles. From A to B to C. Good job. I'm going to draw this off to the right side as well. We're going to separate the 2 triangles from each other. A, B, C is the bigger of the 2. Okay, my picture might not be perfect, but I hope you see. Here's the larger one, A, B, C. Now there's a smaller triangle as well. We didn't use D and E, so right next to that, I'm going to try to pull out that smaller triangle. And it is ADE, like so. So pretend we had like a scissors, right? And we could separate, we could literally cut along the lines and cut out ADE. Then we might see something like this. That's what I wanted you guys to practice first, was just separating the triangles in your mind and naming them. A, B, C, and AD. High five to all of you who tried or who answered. I really appreciate you doing that. Good job. Thanks, Keegan. I see that too. Okay, folks, now what we want to do is label the parts on the separate triangles. So notice on the right side here, I'm going to erase a little bit of the drawing I did on the right, clean it up. Actually, we'll just erase all of it. Okay, now look at the one they gave us, the black and white triangle. See how they've labeled those numbers? They're labeling those segments or like portions of the sides. So for example, DB from here to here is labeled with the 8. So they're telling us that that's 8 units long. EC is labeled as 18 down here, 18 units long. Oh, my bad. Do you see it now, Antonio? Thank you for telling me. Okay, good. So let's do our best to label the sides of our separated triangles on the left. AD is marked as being 20 units from here to here. That 20 means it's going from just A to D. So I'm going to label this over here as 20. Now EC is 18 and DB, D as in dog, B as in balloon, is labeled as 8, but there's nowhere to put that on my separated triangles. But notice how A to B is marked as 20 and 8. So that means this whole section, AB, is 28. Now, because the two triangles are similar, why are they similar? The line cutting through DE has this little arrow, and so does BC. That's a symbol telling us they're parallel. These two lines are parallel to each other. So that means the rule from this page, triangle proportionality theorem, comes into play. Means the triangles are similar because the two lines are parallel. We've got the parallelness here. So that means we can use the 28 side and the 20 side to find the unknown AE. They want us to find AE. That's the unknown here. How long is it? So AE, we don't know that, but we know that EC is 18. We know that A to C is the unknown plus 18. So AC is the unknown. Let's call it X plus 18. We can call it whatever you want. I'm just using X because it's pretty common to use as our unknown. And then AE is just X, just the unknown. So now we've got enough to find the scale factor to go from large to small or from small to large. And the truth is, we can pick which one we want to do. Since I think we're going to end up with a fraction either way. So let's just go from small to large. I want to find the scale factor. So what number do I multiply 20 by to get 18? We're comparing the relatable sides like we were yesterday looking for scale factors. So this is just like the work we did yesterday so far, except we had to set up these triangles and solving for this x, this unknown. So 20 times our scale factor, just like yesterday, equals 28. Now, how do I solve this equation I wrote for scale factor, for the unknown scale factor? Divide by 20. It's 20 times the variable for scale factor. So we got to divide both sides. Remember, anything divided by itself, 20 over 20 is 1. We can cancel that out. So scale factor is this terrible looking fraction, 28 over 20. Okay, reduce the fraction if you can. Because they're both even, that means we can cut them in half. So 14 over 10 and 7 over 5. So that's the one we'll use. That's the most reduced version. So our official scale factor to go from small triangle times it by scale factor to get to big is 7/5, 7 over 5. So that means I can multiply any side on the small triangle by 7/5, and it'll equal the it's a comparable side on the large triangle. So let's set that up now with our x's, with AE and AC. So little side x times 7/5 equals x plus 18. Bottom side to bottom side. Okay, now, because this is a fraction, we're gonna, and because we've got x and the fraction together and then x on the other side, let's start this mess by moving our x's together and combining them into one. So here's some good review. We haven't done this together as a group in a while, is just adding fractions and subtracting fractions together. We're basically combining like terms. So what I want to do is move my x's together and then solve the equation we have for x. And then we'll be done with this problem. We'll have AE because AE, the unknown, is x. We labeled it that. So let's minus x from both sides. And what does that leave us? 7/5 x minus x is equal to 18. Now, to add the fractions or subtract the fractions together, this to combine my x's, we're going to multiply 5 over 5 to this single x. So my equation becomes this. And now we can combine these because they're both fractions with a 5 in the bottom. Why can we do that? Because 5 over 5 is just 1. So I could cancel this out and get back to what we just had. So 7 x minus 5x is 2x, 2/5 x. And now we're just one step away. We multiply both sides by 5 to cancel out the fraction. And we've got to divide both sides by 2 to cancel out that 2 times x. So on the left, we have 2, 2, 5 over 5. So 18 times 5 divided by 2. Comes out to 45. And this whole time, x was just what we labeled the AE side, which is the unknown. So now we know that this side here is 45 total.
So if we were to put this in the steps, first find the triangles, and then you would try to find the scale factor,
Correct. Good.
and um, you try to find the missing side from what you got from the scale factor.
Exactly. Whatever side is they want, we need that skill factor first. So that's great, Aaron. Yeah, start by just like you said. You said it perfectly. I couldn't have said it better. Step one, separate the triangle so you know what it is you're dealing with and you know what you have. Good. Step two, find scale factor. We know that because it's in the lesson and it's in like the mastery test later for um, similarity and dilations. We know there's going to be a scale factor, right? But if we didn't know that it had a scale factor to deal with, we would also need to rely on this principle, this theorem.
Okay.
So we were looking for, okay, cool. We have these two parallel lines. The DE line that's cutting across is parallel. And then that allows us to go on and look for scale factor. And then this problem was, I mean, most of the work, I think, when I look at this, most of the work is really down here in the yellow that I did. A lot of it was just dealing with the fractions. They won't all have fractions in them, but it's good to be prepared for that. So I'm glad we got a tougher one with fractions in it. Good question, Aaron. Any other questions right now? Concerns? Okay. Please feel free to ask. I love it when I hear from you guys. Okay, let's look at another one, and then I've got another principle to look at for today, or like rule that will come into play. Here's another question. This is similar. Find the missing length. So the missing length this time is this stretch up here, that little stretch. That's what they want us to find. How long is that? Okay, if it's too confusing to label it all first, I suppose we can skip that portion of the problem by like naming all the vertices. I think that's helpful, just so you know exactly what the triangles are called and what you're going to refer to them by. Um, but let's see here. We do need to call that unknown question mark something so we can solve for it. Something in the chat. Okay, it could be Sela. It could be that. The truth is, though, I'm not sure yet. I'm not convinced yet. It looks like it could be because it does look kind of like this long, right? Which they're telling us is 4. Um, to be certain, we're going to have to use the proportionality of basically this inner triangle, this littler looking one, compared to the whole triangle, which is all of that. So it's going to be very similar to what we just did. So let's, I'm going to separate them out. Let's do our smaller one first. Okay, we know that the left side here is 15. How about the bottom of the smaller triangle? How long is this section that I'm labeling right here? Can we figure that out just by the numbers they gave us? Something in the chat. Oh, go ahead.
10.
Yeah, is that Sela?
Yeah.
Good job, Sela. And Antonio as well. Good job, both of you. Thank you for answering. Yeah, so that's 10. So this is good. We've got two sides already ready to go on our small. Let's pull out the bigger one now and label it with its sides as best we can. They told us the bottom is 14. They labeled that whole stretch 14, so that's good. Okay, now this is where things get weird again. The whole side is not 15 on the left, is it? It's 15 plus the question mark. This whole side, 15 and the question mark. I'm going to call that X again, just to work with it so it doesn't get too confusing as a question mark. So we're going to call this side 15 plus x. Okay, so let's find scale. So Aaron laid it out nicely for us last time. Step one, separate the triangles. Label them as best we can. We have to have two comparable sides, like 10 and 14, with no x's or nothing weird in there. We'll use those to find scale factor. Let me write that down. And then we'll use the scale factor to figure out what they're multiplying by 15 to get 15 plus x. It might be 20, but I'm not sure yet. So let's go through this process and double check. Um, okay, let's find scale factor. So remember, we can go in either direction. I like to go from smaller to bigger, meaning like, well, 10 times the scale factor gives us 14. Um, I would default to that myself, but we can go either way. So let's write that out as a little equation. 10 times s, I'm going to call it s for scale factor, is equal to 14. Divide both sides by 10. Is this the same scale factor we had last time? That's silly. Sorry about that. I didn't catch that. Change it for next year. Okay, so it looks like the scale factor is the same as last time. That's weird, but let's use it. It's what we're using in this question. So our scale factor is 7/5. So we set up our equation. 10, let's write it this way. Small triangle times scale factor gives us large triangle. So that means 15, that's small, times 7/5 is equal to the large side, which is 15 plus x. Okay, this time, uh, at least there won't be any fractions once we do our multiplying. So on the left side here, combining these two guys, 15 times 7 over 5 comes out to 21. Okay, now we're just solving for x, remember. So if it's plus x plus 15, we want to do the opposite to cancel out that plus 15. So we minus 15 from both sides. And then 21 minus 15 is our x. So that means that little question mark space we're looking for is 6 units. Okay, any other questions or comments, concerns right now, please?
Yeah, so the scale factor is how much bigger the other one gets, right?
Exactly. Exactly. In this case and in the last one, the scale factor was 7/5. So, oh, awesome, Sella. I'm glad to hear. Okay, let's check out the next principle, and it's 10:35. So let's see if we get through this. If we don't, then we'll just pause and finish tomorrow. But let's see how far we can get. Here's our next and last like rule for today that we might have to use in our mastery test. Well, you will, but how it'll be the last stuff plus this. So this one's called the triangle altitude. Say it out loud with me at home. You don't have to turn on your mic, but practice using the language. Altitude. Triangle altitude theorem. What does it mean? If an altitude is drawn on a triangle, then all three triangles are similar. So what is an altitude? The altitude is basically the line straight from the top vertice straight to the bottom. It's similar to the idea of altitude like in the real world. If you were in an airplane, your altitude would be like 3,000 feet or something. That means you're straight up from the ground 3,000 feet. So from on this triangle, from the highest point Q straight down, perpendicular to the bottom, this is the altitude. So this is different than the last theorem because there's no line that's connecting two sides. The line that's cutting through is from one of the vertices. It's at Q. See the difference than the last two examples? And it's going straight down to the other side. Now it's saying that all three triangles are similar. So this is kind of like what we were doing earlier. I want you to practice separating the triangles out in your mind or on your paper. Best on paper so you don't lose track of stuff. I'm going to practice this one with you. It's labeled already with vertices, P, Q, R, and S. So we'll need those points to make sense of these three different triangles. So the largest triangle is PQR. I won't, for space, that they're not going to be as big as they are in the picture. Oh, someone's in the chat. Whoa, awesome. Okay, you're probably right, but I need to double check myself. So, nice job, Antonio. Thank you for. So there's our large, and then medium. I'm going to color it in here for a second. Here's the medium triangle. It also, notice that it also has a right angle right here. So this is SQR. Now I am going to change the um, like the direction of it to make sure that they all are lined up in the same way. So if I were to spin around triangle SQR, the medium sized one, so that the right angle is kind of on top, like the last diagram was, then that would be S right here because its right angle is at S. And then its short side is SQ, so this is Q down here. And then R is the pointy side. Okay, nice. Largest is QPR, smallest is QSP. Thanks, Maria. Yes, correct. Smallest is this little guy on the left side, QSP. And I'm going to rotate it again like I did before, just to make the right angle on top. So that way they can all be comparable, and we'll be comparing the right and left and bottom sides properly. QSP. So this time, S is still the right angle vertice right there. Smallest side for QSP is PS. And then over here has to be Q. Now that we've got them separated, let's label what we know. They want us to find the length of the altitude QS. So they didn't label too much here. They said PS is 6. So find wherever PS shows up in our diagrams on the left. So this is 6. And then they also said that PR is 30. And we want to find QS. QS. So let's label that as XR unknown. And there's one more. Did I miss it? Does someone see the one measurement I missed that's kind of hidden from us? We can find SR without them telling us because they told us 6 and they told us the whole length is 30. So that means SR is 30 minus 6. SR is 24. So wherever that pops up on our diagrams on the right, we'll need that as well. Okay, and you know what? I think we're ready to go. Mm, nice. Thanks, Antonio. Good. Okay, the one thing I'm wondering though is there's nothing comparable to the 30. So I'm just double checking my work. Yeah, I don't see that we can like really label QR right here or PQ. So I don't see anything comparable to that. So let's see what we can figure out or use for the remaining stuff we do have. Now remember, we have similarity because we've got a triangle with the altitude made in it. So that means by definition, all three of these are similar to each other. So let's try to use our scale factor to compare our 24 and the x and the x and the 6. So let's go, I guess, from smaller to larger. So looking at the smallest one, SQP, x times the scale factor gives me 24. X times, I'm going to say S for now. Let's see if this shakes out. Gives me 24. My little times scale factor gets me the medium. And X are the same distance or the same like length. They're both measuring SQ, the altitude. So also 6 times S gets me X. Okay, let's see if this works. So this time, I think we're going to have to take both of these. We're trying to find scale factor. We're setting up our two different formulas to find scale factor. Six times scale factor equals x. Sorry, hang on. I made a mistake right here. Six times scale factor equals x. Okay, there we go. That's better. So now if I were to substitute one of these equations into the other, we'll be able to solve for either scale factor s, or I think we could go straight to finding x as well. Let's see what we get. So since the right formula is already solved for x is equal to 6s. So that means I can replace 6s over on the left side with x. So I'm going to plug in this here. So that means I'm going to plug in 6s over there. So let's see what we get. 6s times s equals 24. I've just combined those two different um, equations together. All right, now we have to use a little bit of our knowledge from Math 2A last fall. S times S is S squared. So we have 6 times S squared equals 24. Divide both sides by 6. We want to get S alone. S squared is equal to 4. Take the square root of both sides. S is equal to 2. Okay. So this one was a little different because 6 over x is equal to, ooh, nice. Yeah. That would have been another way to do it, Sella. Very good. And in fact, we'll look at that one next. Um, that principle you're using would work as well. How you set it up as two fractions. Yes. Good job. I have finally found scale factor. We had to do it by substituting one into the other. But now that we know it, we should be able to solve for whatever else we need here. So we want to solve it for x. Let's just plug in 2 in for s in either of our last two formulas. 6 times s is x. So that means 6 times 2 is x. So that means x is 12. And x was our altitude. What Sella did, and let's see, did you put that in the chat for everyone? Yes. 6 over x is equal to x over 30. So what she's doing is another approach we could use for a problem like this, is make two equal ratios. The only thing though, Sella, and if I'm missing something, please tell me. I think for that approach to work, to do the two fractions that you did, we would just need this 30. If we look again at the three triangles we made, we would need the 30 to line up with another number here or here. Like I don't see any information for QR or for PQ. If we did have that information, then we would use the two fractions that you did. We could say 6 is to x as 30 is to PQ. However, though, I think we could. What you're doing, actually, what you're doing does work. If we just focus on the two sides with x24 and 6x. Okay, right here. This side, we have the x side, the SQ, and then we have SP. See, so we have left and left, good. And then we also have right and right. When I say we have it, I mean there's like a number or a variable there. So I'm gonna really quick show what Sella's setting up. It won't be the 30 Sella. I think we'll use the 24. So what she did was said left side is to left side. So x is to 6 as equals 24 is to x. So she started it this way. And now if we solve this equation in yellow for x, we get cross multiplying. So x times x on the left, 6 times 24, what is that? 144. And then you take the square root of both sides, and you get x is 12. You know what? I wish I would have thought about this too. Good job. So since it's already almost 11, I think we're going to stop for today there. So for today, I'm not going to do any more. And in fact, for homework today, since we're not finishing everything, I'm just going to have you guys show me your notes, and I'm going to mark that down for your grade for your participation today. I really like how Sella came up with this idea to do the proportionality. This is just as legitimate as using scale factor. Sometimes scale factor is a little more direct to use. In this question, though, using the proportionality was actually super fast in yellow at the top, and it gets us the same answer. So I'm going to look at the remaining stuff I have for you guys tomorrow, and I want to incorporate what Sella did with the two fractions into the rest of our work for this lesson for tomorrow. So that's it for today. Before you go, I need to take down your attendance, and I need to see any notes you took for your participation grade.
Josiah, what if you did your notes on the Google Docs?
Then send it to me in the Google Classroom. You can share it with me, or you can download it as a PDF and then upload it.
All right.
Okay. I don't have today's like assignment up yet. I won't get it up until like 12.
Okay.
So you guys can send me a picture on Remind. You can send me a download of it, like I just told Manaya to do. If you want to just send it to me as an email, that's fine. But otherwise, load it up into Google Classroom, so I get it somewhere, whether it's in Remind or my email or Google Classroom. All right. I'm
All
gonna
right.
I'm gonna pull up my camera here. So anyone who has their notes on paper, can you send them to me? And if you show me real quick, and if you are doing them digitally, send me something this afternoon. Okay.
All right. Can we leave?
Keegan, thank you, Keegan. And Aaron, high five, thank you. And Delaney, Maria Celeste, awesome, thank you too. And anyone else, if you don't have them on paper, I get it, but send me something that you did digitally or send it to me later. I'll post today's video